Welcome back. This is section 24.2, conduction mechanisms. I want to look at the question, why do charges move inside a conductor? And the answer is, there needs to be the presence of an electric field. So let's zoom in on a wire here, and you can see there's a wire. Now, in order for there to be a current, there needs to be an electric field. So when we have a source of electric power like a battery, it actually sets up an electric field that goes through the wire, as you can see in the picture. If you take this segment of wire, as I've drawn it, between from one end to the other, there is an electric potential difference. And remember the rule that electric field lines, they always point in the direction of decreasing potential difference. So there's that delta V, positive on the left, negative on the right. Now let's think about the force that a charge feels is equal to the electric field that it's in times the charge equals mass times acceleration. And the acceleration is EQ over m. Now when we have an electric field, they don't keep accelerating. So yes, they will start moving from left to right, or the positive current rather moves from left to right, but the charges don't keep accelerating. Why not? Well, because the charged particles collide with ions, losing energy that it gained in the electric field. So the electric field is necessary to sustain a steady current, meaning you turn on the switch and the current starts moving from left to right. But then as soon as you turn the switch off, it will stop moving because it loses so much energy in those collisions. I'm going to introduce to you Ohm's law, and this is what's called the microscopic version of it. If you look up, Google search whatever in a book, Ohm's law, you'll probably see a different version. This is the less well-known version of it, but I want to start with this version. And it is that the current density is equal to sigma times the electric field. Now, sigma is a constant that refers to the material's conductivity. We've come across sigma before in a different context. In previous lesson, sigma was the surface charge density, coulombs spread out per meter squared. This is a completely different sigma, but it's the material's conductivity. It refers to how well the conducting material allows charges, the electrons, to move through it. So depending on what the electric field is, according to this equation, the greater the conductivity, the greater the current density you're going to have. There's that equation again. J, current density, is sigma times electric field. So you can think of sigma as being a measure of how easily the charges can move through the material. If it's a perfect conductor, this would be a superconductor, then it's infinite. If it's a perfect insulator, then it's zero. Now, for example, typical values, copper and silver have a conductivity of about 6 times 10 to the 7th, and the units are ohms meters to the -1, and that's typical of conductors. An insulator, this would be a very low conductivity, like rubber, would be on the order of about 10 to the -16 ohm meters to the -1. Now, there's a class of materials called ohmic materials. And by the way, this word ohm, it's named after George Ohm. And I didn't even introduce to you this variable here, or this unit. It's the ohm. That's actually the Greek letter omega that we'll get to in just a little bit. But named after George Ohm, ohmic materials are ones in which conductivity is independent of the electric field itself, meaning it's inherent to the material. So J equals sigma times the electric field. For an ohmic material, sigma is constant, and this gives a nice linear relationship here if sigma is constant. And this is what we see in most conductors. Now there's also materials that don't obey that mathematical rule, and they are non-ohmic materials. in which sigma, the conductivity, is actually a function of the electric field. You change the electric field, and that actually changes the conductivity within the material. So there's a nonlinear relation that comes from this equation. The examples of this are semiconductor diodes, battery acid, and ionized vapor that's in mercury fluorescent lamps. What is more commonly thought of instead of conductivity is the opposite of it, resistivity. Resistivity, we use the Greek letter rho, and it's just the reciprocal of conductivity. So if a material like an insulator has a high conductivity, then it has a low resistivity, and the other way around. An insulator has a low conductivity, sigma, so it's got a high resistivity. The units are ohm meters. And now let me introduce to you officially what an ohm is. It's named after George Ohm. He was a German scientist who lived between 1789 and 1854. An ohm, we use the symbol omega. As a general rule for units in physics, we use a letter, and if it's named after somebody, generally it's the first letter of that person's name, and it's capitalized. But we're not going to use the capital letter O. We shy away from using O, which would stand for George Ohm, because O looks too much like zero. And so rather than using the letter O, we use the capital letter omega. By definition, an ohm is a volt per ampere. And as we go on in this chapter and in the next chapter when we study electric circuits, we'll see that relationship, that an ohm is a volt per ampere. So you've previously learned in this lecture that the current density J is sigma times the electric field. And now we're going to say that it's the electric field divided by resistivity. So the higher a material's resistivity, the stronger the electric field is needed to produce a given current density. Now, typical volumes, aluminum is 2.65 times 10 to the negative 8 ohm meters. Copper is about the same, 1.68 times 10 to the negative 8 ohm meters. Gold and silver, you can see all those that are very good conductors of electricity. Here is from the book a table of resistivities in ohm meters. And you can see some of those I mentioned on the previous page, but metallic conductors, and all of these are at given temperatures. So it says at 20 degrees Celsius. What we'll see later on is that resistivity can be temperature dependent. Then you have ionic solutions in water at 18 degrees Celsius, and you can see they are more resistivity, meaning they're not as conductive as those metal conductors. But you can see, for example, hydrochloric acid, sodium chloride, so a salt solution with water, and on down. And by the way, here's H2O, which has, notice it's 2.6 times 10 to the fifth, as opposed to some of these others, 10 to the negative 2, negative 4, so it is very, very highly resistive. And then you have insulators, ceramics, glass, rubber, somewhere between 10 to the 11th and 10 to the 17th ohm meters. Let's look at an example in the book, example 24.3, finding the electric field in household wiring. A 1.8 millimeter diameter copper wire carries 15 amperes to a household appliance. Find the magnitude of the electric field in the wire. Well, there's the radius, 0.9, half the diameter, times 10 to the negative 3 meters. Current is 15 amperes. We look up on the table in the book. Copper has a resistivity of 1.68 times 10 to the negative 8 ohm meters. The question is asking, what is the electric field? We say that current density is electric field over rho, which means electric field is current density times resistivity. Remember that current density is current over area. So plugging all those in, we have the current of 15 amperes. The cross-sectional area is pi times the radius squared. And then we're going to multiply by the resistivity. What we end up with is 0.099 volts per meter, or we can say 99 millivolts per meter. So copper is a great conductor used for wires, which means it doesn't take much electric field to drive a large current through it. Looking microscopically, or continuing to look microscopically, conduction in metals. Metals are good conductors because they contain many free electrons which respond readily to electric fields. Each atom in a metal typically contributes one or more electrons to this sea of free electrons. So here we have a picture of a crystal lattice, atoms of a metal. And so it's a lattice of ions plus free electrons, and as I said, usually one or more free electrons per atom. The electrons move through the lattice at a very fast speed, typically about 10 to the 6 meters per second, and they collide with the ions on the way. If there were no electric field, then there would be just random electron motion and therefore no current. But then we turn on the switch. We have it hooked to a battery, a source of an electric field. And there's still much random collision, but there's a slight drift against the electric field. Here I've drawn the electric field going to the left, which means positive current is going to the left. But remember, the electrons are negatively charged, so they're actually moving to the right. And here in this picture, you can see they're moving very fast, about 10 to the 6 meters per second, but they keep colliding and bouncing back and forth with a gradual drift to the right, and that's what the drift velocity is. Let's now talk about electric current in liquids, so ionic solutions. Liquid solutions contain positive and negative ions that respond to an electric field by moving in opposite directions. If you look at this picture, I've drawn the electric field going to the left. The positive ions will go to the left, and so they have a net current to the left. The negative ions will go against the electric field, so they have a net current, or they are moving to the right. But since they're negative, that means they are contributing a positive current to the left as well. And so we have a net current to the left. Conductivity in the ionic solution is limited by collisions between ions and neutral atoms. They are poorer conductors than metals. You can see in the table of resistivities and down below the partial table, it's not quite as low resistivity as metals, but still many of them are pretty low. Now the question, does water conduct electricity? Sort of yes and sort of no. Pure water, pure H2O, you can see it at the bottom of the page. It's actually a terrible conductor. It has a very high resistivity. But most water that you will run across in everyday life, like tap water, water in a lake maybe, then yes, because it has minerals in it. And so it is a good conductor of electricity. So there are safety hazards involved with mixing electricity, electric wires, and most water that you come across in everyday life. Maybe a spill, water on the floor, that can be dangerous electrically because tap water, and again, as I said, most water that you will come across in everyday life has minerals in it, and it does conduct electricity very well. I haven't prepared a video on this, but it would be good for you to read in your textbook the section, it's just 2 pages, on plasmas, semiconductors, and superconductors. As I close out this section, I want to do 2 problems in the end of the section, or the end of the chapter. Let's look at number 14. It says a 12-volt car battery is rated at 80 ampere hours. meaning it can supply 80 amperes of current for 1 hour before it becomes discharged. If you accidentally leave the headlights on until the battery discharges, how much charge moves through the lights? All right, so we've got 12-volt battery, 80 ampere hours. Let's think of that as that the amount of charge is 80, and instead of calling it amperes, let's think of it as coulomb per second, then times hours. That's the total charge. We can then say current is Q over T, but we want to know what is Q. We want to find that charge. So charge is current times T. And the current is 80 coulombs per second, and then times hours. And then we're going to convert hours into seconds. So 3,600 seconds divided by hours, and that's 2.9 times 10 to the 5th coulombs. Problem number 15 says biologists measured the total current due to potassium ions moving through the membrane of a rock crab neuron cell as 30 nanoamperes. How many ions pass through the membrane each second? So we have 30 nanoamperes. Remember that amperes is coulombs per second. So let's say 30 times 10 to the negative 9 coulombs per second. And then we're going to multiply by, or we're actually going to do the conversion. An ion is one elementary charge. And so think of it as the charge of a proton. And then we're going to convert that one of those is 1.602 times 10 to the negative 19 coulombs. So the coulombs divide out, and we're left with how many of these ions pass per second. And we get 1.9 times 10 to the 11th ions per second. Let's do another problem in the back of the chapter. Number 42 says, there's a 2.5 volt potential difference between opposite ends of a 6 meter long wire, iron wire, 1 millimeter in diameter. Assuming a uniform electric field in the wire, find the current density and find the total current. Here's the given information. We have a voltage difference of 2.5 volts. The length is 6 meters. We'll note that it's iron. And the diameter is 1 millimeter. We want to find current density and the current. For current density, we recognize current density is electric field divided by resistivity. But we want to know what is the electric field. Remember, electric field is electric potential difference between 2 points divided by the distance between those 2 points. So it's a 2.5 volt difference over a 6 meter length of wire, and that gives us an electric field of 0.416 repeating volts per meter. Now we're going to plug that into this equation for current density, E over rho. Well, there's E, the electric field, 0.4166 volts per meter, divided by rho, the resistivity for iron. We look that up in the table. We get 9.71 times 10 to the negative 8 ohm meters. And we're left with 4.29 times 10 to the 6th. And you look at what happened to the units. It was volts per meter divided by ohm meters, which is volts per ohm meter squared. Now, a volt per ohm is an ampere. So we're going to say that that's amperes per meter squared, which is exactly what we expect current density to be. Remember, it's current divided by area, amperes per meter squared. Then once we know that, current is just the current density times area. So we know J, the current density, times pi r squared. Make sure you turn R. We have a diameter of 1 millimeter. So cut that in half, 0.5 millimeters, and then let's get it in meters. So 0.5 times 10 to the negative 3 meters, pi r squared, and we get 3.37 amperes. Another example is question 44. Silver and iron wires of the same length and diameter carry the same current. How do the voltages across the two compare? All right, so here I've drawn silver and iron, same length, same radius, same current. What about the voltage difference across them? Well, the voltage difference is going to be the electric field times the delta x, the difference between the 2 points, which is electric field times length. Also remember, electric field is J over rho. And remember what J is, the current density, I over A. So the electric field is I over A rho. Now substitute that into the voltage equation. If voltage is electric field times length, then we can say that voltage is current times length over area over rho. And then we can see that when we take this equation and we want to see what is happening to voltage, let's use this technique where we take the equation and let's allow for that some things will be variables, some things will be constant, and let's throw the constants to the right. So in the setup to the problem, it said that same length, same current, same size, meaning area, those things are constant. But between silver and iron, they have different resistivities. So this equation in black becomes the equation in purple, that voltage times rho is IL over A, which is constant. Let's ignore IL over A, and we'll just say voltage times rho is constant. So now we have V of iron times rho of iron equals V of silver times rho of silver. Setting that up as a ratio, we can say V of silver over V of iron is rho of iron over rho of silver. And then we can set those up, plug in those resistivities, and we get a ratio of 6.11. So the voltage through the silver is actually going to be 6.11 times the voltage through the iron. So the question asks, how do the voltages across the two compare? Well, it's a 6.11 to 1 ratio. Another way you could solve this problem, what I've done here in the green, is just to take the equation in black, where my red pointer is at, and just set up a ratio of voltage through the silver over voltage through the iron. And then it becomes the IL over A rho of silver divided by the IL over A rho of the iron. So you're going to multiply by the reciprocal of that. You see all the things that are going to divide out because current through the silver, current through the iron, those are the same. Area of the iron, area of the silver, those are the same, as are the lengths. And what you're left with is the ratio, the same solution that I got over here in the purple ink. And you still get the ratio of those resistivities. So 6.11 to 1 ratio. That concludes section 24.2. Have a great day.